In a previous video, we've looked at the idea of force and how forces can be observed, how they can be calculated, and how you deal with multiple forces. Right? Force is a vector quantity where direction matters, and we came across the ideas of equilibrium, right, where the sum of all the forces are equal to zero and the acceleration is therefore zero. And the framework we've built up works for any set of forces. So what I'd like to do now is look at two types of forces that can crop up in our everyday life. Now, these aren't special in the sense that they are forces. A force is something that causes a change in velocity, but they are physical situations that it's worthwhile knowing a bit about. So the first of those is friction, and in this video we'll just look at some of the basic ideas associated with friction. And we'll start off with zero friction in the system. All right, and we'll push on the box, and we'll see right now the box is in equilibrium. The sum of all forces are equal to zero. If we start pushing, all right, we push on it, we apply 191 newtons, and we've got 191 newtons on the box, and we take away the force, and Newton's first law tells us in the absence of a force, an object will keep moving at constant velocity, and that's what the box is doing. There's no friction, so the box will keep on going forever unless there's a frictional force. And so the frictional force opposes the motion. So frictional forces oppose motion. We're going to have to be really careful with that later on, but keep that in mind. Frictional forces oppose motion. And eventually, that frictional force causes the object to stop. Now, it turns out that frictional force is going to depend in some way on the properties of the box. We'll have to work out what those properties are. So let's have a look at that. Let's push on this box again. All right, we'll put some friction in. And we'll push. Now, while the box is stationary, as we increase the pushing force, the applied force, the frictional force increases by exactly the same amount. So if we double the applied force and we don't move the box, then the frictional force has doubled. And the frictional force will match the applied force up to the point where the box starts to slide. All right, and there, somewhere there, we've started to slide, and now you'll see that the applied force is different from the frictional force. All right, and there's a net force of 35 newtons in this case, and so the object is accelerating. If we take away the applied force, then there is only the frictional force, and that's constant until the box stops. All right, and then all the forces add up to zero again. Let's put a different object there, and we'll start pushing on that. And I push harder and harder and harder and harder, and it's still not moving. We're beyond the point where we were before with the 50 kilogram box. We've got bigger. Still, you'll notice the applied force is equal to the frictional force. They're equal in size and opposite in direction. These are not reaction-action pairs. We'll talk about the origins of these forces in a while. All right, so we keep on pushing, 282 newtons, 282 newtons, still the box is stationary. Still, geez. And that's as far as I can go. I can't apply any larger force on there. Let's try that again. 500 newtons and it's still not moving. Let's go back to the box. I think we'll go in the opposite direction now. We start moving somewhere. somewhere above 115 newtons. So it turns out the size of the box makes a difference. I think we'll change the coefficient of friction, just decrease it a little bit. And we'll push and push, and it starts moving. Let's see if we can get the refrigerator moving. All right, what we did was change the way friction interacted with the fridge. So we'll have to look at what causes that. So it turns out that the amount of friction depends on the mass of the object in some way. All right, and that's probably not a big surprise to you. It's much harder to move a big, heavy object along the ground than it is a small, light one. So we're going to investigate what the origins of these forces are, how we can describe them mathematically, right? And then look at a couple of examples of how they're used.